Have you ever wondered what the future of computing looks like? Forget faster processors and more RAM. We're talking about a completely different league of technology, one that could solve problems we currently consider impossible. Today, we're diving deep into one of the most exciting developments in this field. Microsoft is Majorana quantum chip. This isn't just an upgrade, it's a revolution. So, what makes this little chip so special? Stick around, because we're about to unlock the secrets of a technology that could change everything. First, let's get a quick refresher on quantum computing. Classical computers, like the one you're watching this on, use bits. A bit is a simple switch, either a 0 or a 1, it's on or it's off. Quantum computers, on the other hand, use quantum bits, or qubits. Thanks to a wild quantum phenomenon called superposition, a qubit can be a 0, a 1, or both at the same time. This ability to exist in multiple states at once is what gives quantum computers their mind-boggling power. Imagine trying to find your way through a massive maze. A classical computer would try one path, hit a dead end, go back, and try another. A quantum computer could explore all possible paths simultaneously. This parallelism is the key to their incredible potential. But there's a huge catch. Qubits are notoriously fragile. They are incredibly sensitive to their environment. The slightest vibration, temperature change, or even a stray magnetic field can cause them to lose their quantum state in a process called decoherence. This is like trying to build a sandcastle during a hurricane. As soon as you make progress, a wave of errors comes and washes it away. This fragility, this error problem, has been the single biggest roadblock for quantum computing. For years, scientists have been trying to build more stable qubits, but it's been an uphill battle. This is where Microsoft's approach completely changes the game. Instead of just trying to build better, more isolated qubits, they went back to the drawing board and asked a different question. Is there a way to build a qubit that is naturally protected from errors? Their answer lies in a strange, almost mythical particle, first predicted back in 1937, the Majorana fermion. Now, this is where things get really fascinating. A Majorana fermion is its own antiparticle. Think of it like a coin that's both heads and tails at the same time. What's truly special about them is how they store information. In Microsoft's chip, they don't use a single Majorana particle as a qubit. Instead, they use a pair of them, separated at a distance. The quantum information, the 0 or 1, isn't stored in either individual particle. Instead, it's encoded in the relationship between the two in their combined state. This is what's known as topological encoding. Imagine you have a piece of rope. You can tie a knot in it. The knot exists as a property of the entire rope, not just one specific point. You can jiggle one end of the rope or nudge the middle, but the knot itself remains. You'd have to cut the rope to undo the knot. This is the genius of the topological qubit. Local disturbances, the little nudges from the environment that would destroy a conventional qubit, don't affect the stored information. The information is non-local. It's spread out and protected by the very structure, or topology, of the system. This makes the Majorana qubit inherently robust against decoherence. It's like building your sandcastle with a special kind of magic sand that automatically repels the waves. This intrinsic error protection could be the breakthrough we've been waiting for. So how did Microsoft actually build this? It's an incredible feat of materials, science, and engineering. They created a nanowire made of a semiconductor and a superconductor. When they applied a specific magnetic field to this wire, they were able to coax these exotic Majorana particles into existence at the ends of the wire. For a long time, this was just a theory. But earlier this year, after a decade of painstaking research, Microsoft published a paper with compelling evidence that they had finally done it. They created and measured these topological qubits. This is not just an academic achievement, it's a practical engineering milestone. Microsoft didn't just find a Majorana particle, they created a device, a physical chip, that can reliably produce and control them. They've essentially built the fundamental building block for a new type of quantum computer. A topological quantum computer. This is huge. While other companies are focused on adding more and more noisy, error-prone qubits and then trying to correct the errors with complex software, Microsoft is building a system that's clean from the ground up. Their goal is to create a qubit so stable it might require far less error correction. maybe even 1,000 times less than other approaches. Let's talk about what this means for the future. A fault-tolerant quantum computer could revolutionize fields we can barely imagine. In medicine, it could simulate complex molecules to design new drugs and treatments for diseases like Alzheimer's or cancer in a fraction of the time it takes today. In materials science, we could discover new superconductors that work at room temperature, leading to perfectly efficient power grids and levitating trains. For climate change, a quantum computer could help us develop new catalysts to capture carbon from the atmosphere or create more efficient batteries. The possibilities are truly transformative. Of course, we're not there yet. This is still the beginning of the journey. Microsoft has demonstrated the fundamental building block. The next step is to scale it up. They need to figure out how to put many of these topological qubits on a single chip and make them interact with each other to perform complex calculations, a process called braiding. Think of it like literally braiding the paths of these Majorana particles around each other to execute logical operations. It's a complex dance of quantum physics that will require even more engineering innovation. But the foundation has been laid. Microsoft's achievement represents a major philosophical shift in the quantum race. It's a move from a more is better approach, just adding more noisy qubits, to a quality over quantity approach. By focusing on creating a fundamentally better, more stable qubit, they may have found a more direct path to a truly useful, large-scale quantum computer. It's a long-term bet that is now starting to show incredible promise. So, while we won't have a topological quantum computer on our desks next year, this breakthrough is a pivotal moment. It validates a decade of theoretical work and opens a new, very promising path forward. Microsoft's Majorana chip isn't just another piece of hardware. It's a beacon of hope for solving some of humanity's greatest challenges. It's a glimpse into a future where the word impossible starts to lose its meaning. The quantum leap forward is no longer just a theory. It's happening right now on a tiny, super-cooled chip in a Microsoft lab. What do you think? What problems would you want to solve with a quantum computer? Let me know down in the comments. It's an exciting time to be alive, witnessing the birth of a new era of computation. Thanks for watching, and if you enjoyed this deep dive into the future of tech, make sure to like, subscribe, and hit that bell so you don't miss our next video. See you!